Hey everybody, it's Mr. Oliver. I'm going to go over the solutions for the AP Physics 1 Unit 3 review practice, and let's go and get started. So this first question talks about a spring that's setting on, or a mass that's setting on the spring, and it compresses it to some new position. So we start at A, end up at B, and it wants to know the change in energy of the block spring Earth system. So let's look at this. What kind of energy do we have at the beginning? Well, it starts off with an uncompressed spring, but this mass is at a distance of 30 meters above the ground. So it does have gravitational potential energy at the beginning. So its initial energy type is mgh initial. So we can calculate that real easy by taking the mass, which is 4 times 9.81 times this initial height, which is 0.3 meters. Remember, convert to centimeters to meters, and you get 11.772 joules initially. Now afterwards, after this thing has come down, it now is at a new height, but you've also compressed the spring. So its final type of energy is mgh final plus some amount of spring potential energy or elastic potential energy, which is 1/2 kx squared. And so now we know that that spring is compressed from 30 to 20. So this is your distance x, which is 0.1 meters or 10 centimeters. So we substitute our numbers into this final equation. So you'll have 4 times 9.81 times 0.2 plus 1/2 times 500, which is the spring constant, times 0.1 squared. 0.1 squared, it's kind of hard to fit in there. But when you calculate this, you end up getting a final energy of 10.348 joules. All right, so to determine the change in energy, remember delta E is always a final energy minus an initial energy. So we take our 10.348 joules minus 11.772 joules, and you get delta E is equal to negative 1.424 joules. So in this case, this system lost 1.424 joules of energy. Where did it go? I don't know. Maybe the spring heated up. Maybe there was some inconsistencies in our numbers. I mean, maybe there's air resistance. Who knows? But that's the idea of this first one. All right, question number 2. We've got a ball that drops, hits a floor, and then bounces back up. And we want to know the maximum height of the ball after the bounce. So this is kind of a similar kind of scenario. We want to find out what the initial energy is, what the final energy is, and then figure out how much height has changed between the two. So it tells us that during the bounce, you dissipated 0.6 joules. So that's our delta E. For this case, we lost 0.60 joules. So this needs to be a negative energy. Now our initial energy, once again, is just a potential energy due to gravity. And so when we substitute our numbers m, g, and h into this, I'm going to use the height of 1.5 meters. That's my initial height. And you end up getting 2.943 joules when you substitute those numbers in. And so what I don't know is what my final energy is. So the final energy I can actually get from this relationship for delta E. Because remember, delta E is a final energy minus an initial energy. So if I calculate that, or rearrange that equation rather, the final energy is going to be my change in energy plus my initial energy. And so I can calculate my final energy as negative 0.6 plus this 2.943, and you get your final energy is 2.343 joules. And so now what I can do is I can set my final energy to equal mgh final, because I know it's bouncing back up to some height. So rearrange this, solve for h. H is going to be energy final divided by mg, and so your final height is 2.343 joules divided by my mass, which is 0.2 times 9.81. And you end up calculating 1.194 meters. So that's how high that bouncing ball ended up going back up. All right, so this question number 3, kind of a conceptual multiple choice kind of question. You've got a sled sliding down a hill with friction between the sled, but there's no air resistance. Which of the following must be correct about the resulting change in energy? Well, the easiest way to think about changing of energies when you're talking about things moving, just remember that the change in energy is always equal to the work. Okay, this is what we call the work energy theorem. All right, so in this case we say, okay, well, what my change in energy is, I got to figure out what kind of work I have done. Well, the work is done by friction. All right, that's where you lose the energy. All right, there's also work done by gravity, other kind of factors, but in this case, any change in energy has to come from the frictional forces. So therefore, the energy that you dissipate as heat accounts for that change of kinetic and potential energy. So just remember that this frictional force changes not only just the potential, not just the kinetic energy, but also affects the potential energy. So it changes the gravitational potential energy, and it also changes the kinetic energy. And so the only solution, or the only choice that answers with this one, is the sum of the kinetic energy and the gravitational potential energy changes by an amount equal to the energy dissipated by friction. So your answer choice is A, right here. All right, that's question 3. Question number 4. You've got a kid with a spring scale, and we want to sketch a graph of the force as a function of distance and also determine how fast the block will be moving. Okay, so first thing, easiest thing is look at that force. The force is a constant 10 Newton force. It doesn't change with distance, it's always 10 Newtons. So the graph will be pretty easy. We just sketch force versus displacement, x. And so that's just going to be a nice little straight horizontal line at 10 Newtons. All right, and the question asks, well, how fast is it going to be moving when we get to 0.5 meters? Well, 0.5 meters may be over here somewhere, and so I want to know how fast it's moving. Well, as long as I can figure out an amount of energy that happens during this time, then I can set that energy amount equal to the kinetic energy. And if you remember, kinetic energy has that speed term in it. So if I can find the kinetic energy and I know the mass, I can find how fast it's moving, this v. Well, the way I can get the kinetic energy is by finding the work, because remember, work changes energy types. It changes, in this case, the kinetic energy. Well, the easiest way to get work is by taking the area of a force versus displacement graph. That's a big key point here, is that work is the area of a force versus displacement graph. Not force versus time, be careful that, a force versus displacement graph. Well, in this case, the work is just going to be 10 newtons times 0.5, so the work here will be 5 joules, which then I can set equal to 1/2 mv squared. Really, it's 1/2 mv final squared minus 1/2 mv initial squared. But because it started from rest, there is no initial kinetic energy. So I'll take this little relationship right here, solve for v, and y'all can do the algebra on your own, and you end up getting 2 meters per second. That's how fast it's moving after it's gone 1/2 meter. All right, 2 meters per second. All right, number 5 is kind of along the same lines. You've got a graph of force versus displacement, and you want to find the change in kinetic energy. What is the net change in kinetic energy? Well, that's simple enough. The change in kinetic energy is equal to the work, and the work is equal to the area from, in this case, 0 meters to 4 meters. So looking at this graph right here, we want to find the entire area of this graph. Now, because this first little box right here is above the axis, this will be positive. But the second box is actually below the axis. And so because it's below the axis, the height of the box is negative 5 meters. So this will be a negative 5, or negative energy, sorry. So right here, if I have 2 times 10, this will be a positive 20. Right here, I've got 2 times 5, that's going to be a negative 10. And so for this particular case, the change in energy is 20 minus 10, or a change in energy equal to 10 joules, positive 10 joules. All right. And I think usually when you see these force versus displacement graphs, it should immediately pop into your head what's going on. Number 6 is one more question kind of along the same lines. Even though we're talking about a spring, it's still a force versus distance kind of term. So if you want to find the work due to the spring, then that would be the same thing as the change in kinetic energy. All right. So if I could find that work, then I could figure out how fast it's moving, or find out what's going on. So here's the thing. I don't know enough information about what's going on. And guys, this goes on to the next question, by the way, on the next page. Sorry. All right, so I don't really have much information. I can't tell much what's going on, but I can find the area. And so what I'm going to do is I'm going to find the area, and we can approximate it. It's not exactly perfect, but it kind of looks like a triangle. I'm just going to draw a straight line here. And so this area would be the work. And so in this case, it's going to be the work due to the spring is going to be 1/2 the base times the height, which is just 1/2 times a length or a base of 0.1 times a height of 60. And so that's going to be equal to 3 joules, which will equal the change of kinetic energy of that object. All right. Now number 7. Okay, we just did that one. Delta K, approximate the kinetic energy. So delta K we said was 3 joules. Okay, done. Number 7. Number 7 is a pretty classic conservation of energy problem. So this is a little bit more involved. So let's start off like this. Let's sketch out the free body diagram acting on this block real quick. All right, so there's my incline, here's my block. I've got 3 forces that act on this. I've got a force of gravity, which is m times g, mass times g, pulls straight down. I've got a normal force, which is always perpendicular to that incline, goes this way. All right. And I'll also have some friction. And that friction, because the block is sliding down the hill, the friction has to go up the hill. So the first thing I want to do is, because I know I'm going to need it eventually, I need to find something out about normal force, because friction depends on normal force, right? Friction is equal to the coefficient of friction times the normal force, right? Well, in this case, the normal force has to have some kind of component that opposes it. And it's this component that goes down into the ramp. This is this mg cosine component, right? Where the angle theta here is the same angle as the ramp theta, all right? So in this case, Fn will be mg cosine theta. All right, so there's an expression for friction, which I'll know I'll need. All right. Now, in order to find the kinetic energy, the final kinetic energy, determine the kinetic energy of the ramp, of the box at the bottom of the ramp. So I want to find out how much kinetic energy it has down here. So I'll use conservation of energy for that. Get up here, we can see it. E initial is equal to E final. The initial energy will be gravitational potential. The final energy will be kinetic energy. But because there is friction, that frictional work is going to take away from the entire system energy. So the way you usually do this when you deal with friction is you put that negative frictional work term to the left of the equal sign. And so this final kinetic energy, which is what we're looking for, is just going to be my gravitational potential minus my work due to friction. Well, the gravitational potential is just mgh. And the work due to friction is the frictional force times the displacement. All right, well, I already found the frictional force. It's mu mg cosine theta. So we're going to have mgh minus mu mg cosine theta. That's my friction right here. And then the distance that it travels is going to be the length L. And that equals my final kinetic energy. All right, which is all it's asking to find. And it says to put it in terms of variables and fundamental constants. So let's just make sure that all these letters show up in the problem. So first of all, there's an m, so there's a mass m, so we're good. G is a fundamental constant, so we can use that. H is given, that's this. Mu is given right here in the problem. Mass once again, G once again. Theta is given right here in the picture. It says it in the problem as well. And then the length L is also there. So this is a valid solution for this problem in terms of the given stuff. All right, number 7 down. Number 8, we've got kind of a multi-step problem, problems 8 through 10. First of all, we've got a ramp with a cylinder at the top of the ramp. So imagine like a can of beans or something rolling down this hill. And this ramp is 1 meter high, and then once it gets to the end of the ramp, it's going to take a leap of faith and jump right off this and hit the ground 1.5 meters away from a height of 1 meter. All right. So the question asks, there's a lot of calculations we can do with this, but I wanted to show you this where you don't really always have to have calculations. The question says, as the cylinder rolls down the ramp, how do the potential energy of the cylinder or system and the kinetic energy of the cylinder change? Increase, decrease, or no change? All right, so first of all, obviously, as it goes down the ramp, the potential energy goes from a high value, because it's above the surface, to a low value. So the potential energy due to gravity decreases because the height decreases. Now, what about the kinetic energy? Well, the kinetic energy has to increase. And the reason why it increases is because it picks up speed. Well, where did that speed come from? It came from the potential energy that it had. You can't just generate energy out of nothing. What's happening is that potential energy converted into kinetic energy. Is it 100% conversion? Who knows? But for right now, we just know that it's converting from one type into another. Okay, question number 9. After the cylinder leaves the table, but before it lands, how the rotational kinetic energy and translational kinetic energy change? Well, this is something we really didn't talk that much about, but just think about it. While this cylinder is in the air, it will have been rolling down this hill, right? So that you can imagine that can just kind of rolling around, rolling. And so when it's up here in this air, let's look at that kind of close up. When it's up here in the air, it's not only translating, it's actually got some kind of a parabolic path that's moving down. We call that a translation, okay? But it's also rotating. It's rotating around its central axis. So it's got two kinds of motion while it's flying through the air. And so the question is, how do these kinetic energies associated with this change? Well, the translation is pretty easy. It's going to pick up speed because gravity pulls it down, right? The side-to-side motion, because it's a projectile, doesn't change, but it does get faster going down. So the translational kinetic energy increases. But this rotation, remember, rotation comes from torques, and torques involve things that make it want to spin faster or slow down. Well, there's nothing while it's in the air to make it slow down. There's no friction, no air resistance, nothing. And so that rotation, that thing's just going to keep spinning at the same rate at which it left. So the K rot, sometimes they call it, is no change while it's in the air. It's almost, imagine like a wheel or something with a frictionless bearing. Is that once you get it spinning, it's just going to spin forever. It's always going to have a rotational kinetic energy. All right. And then question number 10, a sphere with the same mass and radius as the original cylinder but smaller rotational inertia is released from rest. Ks and Kc are the spheres and the cylinder's total kinetic energy at the bottom of the ramp, respectively. How do these kinetic energies compare? Well, this is kind of a trick question a little bit. They're going to be the same. Kc is equal to Ks. And the reason why I know that is because they both would have started with the same potential energy. Sphere, cylinder, whatever you have at the top, they still start at the same height. So the gravitational potential energy here is the same for all objects. And that energy's got to turn into something, and it's got to turn into kinetic energy. Because both have the same initial potential energy, they both have the same final kinetic energy. It's just a simple statement of E initial equals E final. E initial is mgh, E final is K of the system kinetic energy, whatever you have. Doesn't matter what it is. Right? Now, question number 11. This is a good little simple pendulum problem. Use conservation of energy here. We've got this pendulum starting at 1 meter. A little bit later, it's going to move down to 0.8 meters above the floor. So it's going to kind of come through to some lower height. Not straight down, but a little bit lower. So 0.8 meters will be its final height. And we want to calculate its speed. So let's just use E initial equals E final. My initial energy type, it's raised to this amount and then released from rest. So it all has only gravitational potential energy at the beginning. At the bottom, at this 0.8, it's going to be moving, but it's also going to have some potential energy there as well. So it's going to have both potential and kinetic energy types. Now what's nice here, even though the mass term is included, we really don't even need it because it's going to cancel. That mass term shows up in every term. And then really all I need to do is solve this equation for my final velocity Vf. All right, so I'll take this gh final, move it to the left. So I'll have gh initial minus gh final, and that equals to 1/2 v final squared. Multiply everything by 2 on both sides, gets rid of the 1/2, and then we'll take the square root to get rid of the square term up here. And you can substitute your values in, calculate it, and you should get around 2. It's like 1.981 meters per second. Alrighty, then question number 12. We've got a block sliding down this hill, and you've got these two forces applied to it while it's sliding. All right, so it's not only gravity pulling it down, but you've also had these extra little applied forces. You got a vertical force and a horizontal force. So the question says, when the block reaches the bottom, the block Earth system has a mechanical energy E0. The experiment is repeated, but now horizontal and vertical forces magnitude F are exerted on the block while it slides, as shown above. When the block reaches the bottom, the mechanical energy of the block Earth system, I'm going to add, does it increase, decrease, change? What happens? Well, whenever I have forces applied, as happens in this scenario, we got to ask ourselves, what do forces do? Well, forces do work. Now, if you remember, work changes energy. All right, so what we need to do is say, well, are these forces going to add energy to the system, or are they going to decrease energy to the system? Well, the easiest way to think about it is think about how you calculate work. Well, if I look at this block, that block is going to be moving down this incline. It moves down this 30-degree incline. Okay, so that's my displacement. That's my displacement vector. It's moving down that direction. Well, if I left it to gravity, friction, whatever natural things happen, they're going to be exactly the same in the original scenario as it will be in the secondary scenario. So I'm not even going to draw the gravitational force. I'm not going to draw the normal force on here because they're going to be the same in both cases, both before and after these forces are applied. But then what I'm going to do is I'm going to say, okay, well, these applied forces, if I look at them kind of independently, it's kind of like I've got two vectors added together and my net force kind of goes up at this 45-degree angle. So if I were to sketch this out on here, this combination of these two instead of doing independent ones, that net force goes at a 45-degree angle. All right. So a 45-degree angle, if this is 30 degrees, is going to be 15 degrees from this vertical right here, right? Because if this is 30, this right here would have to be 60 degrees, and this would have to be 15 degrees. All right. So if you think about it, this 15-degree angle is pointed slightly downhill. This angle right here, this 75-degree angle, is that right? Yeah, 75-degree angle is mostly helping to push down the hill. In other words, if I were to calculate the work, F d cosine theta, then this F net times that displacement times the cosine of 75 degrees, this is going to give us some positive value of work. It's adding energy to the system. And so when the block reaches the bottom of this hill, it's going to have more energy in this new scenario than in the original. Guys, I'm off page, I'm sorry. Okay, so in this particular case, yeah, it does add energy to the system. If we had a different scenario with a different set of forces, maybe that net force pointed up like that. And so in that case, you'd end up having an angle that's greater than 90 degrees, in which case you'd calculate a negative work and it would take energy away from the system. So it's kind of a tricky question. This is one of those AP Physics 1 questions that are a little bit more complicated than we need. But just think about it like this. If you have any amount of force that helps push you down the hill, you're going to gain energy. If you have any amount of force that keeps you from going down the hill, you're going to lose energy. And that's usually the best way to think about it. All right, question number 13. We're almost done. Last page here. An apple is dropped from rest from 500 meters up. So let's go ahead and calculate its initial energy, which is going to be mgh. So that's, I don't know how mass is. So let's do this. Let's make up a number. Let's let the mass be 1 kilogram. That's kind of a heavy apple, but we'll say it's 1 kilogram. So if I calculate this is 1 times 9.81 times 500, which would give us an initial energy of 4905 joules. Okay. Well then, if it says due to the combined forces of air resistance, gravity, we have a final speed, so we can calculate a final kinetic energy because all this potential converts to kinetic. And so it's going to be 1/2 mv squared. So we'll keep the same mass, and it doesn't really matter what the mass is. We're just using a made-up number here. 1/2 times 1 times 40 squared is 800 joules. Okay, so you can tell that it lost a lot of energy when it was falling. And the question is, what is the percentage energy loss when what percentage of the initial mechanical energy was dissipated? All right, so if you remember, percent is always going to be a small number over a big number, but percent lost is 1 minus the small number, in this case 800, over the big number, 4905, times 100. That's the percent energy lost in any kind of a problem. And so when you calculate that, you get about 84%, 83.69% was lost due to air resistance. All right. Question number 14. We have a projectile launched from this initial height, and it's going to fly through the air. So if I were to sketch this out, it's going to have this kind of parabolic shape, and then fall down here and hit the ground. Okay. Well, the one thing that's good about parabolas is that they're symmetric. So that means that if I were to come over here to the same height from which we launched at, which is what the problem statement says, that I'm returning to the same height, h naught, we want to determine the work done by the gravitational force. So if you think about it, if this projectile was launched right here with some initial speed, let's say it's 10 meters per second, because of that symmetry, that projectile will be moving at 10 meters per second down and to the right at that same height. So you got 10 here, you got 10 here. So the kinetic energy would be the same, right? In other words, the change in kinetic energy is 0. It's moving the exact same speed. And in fact, it will have the same potential energy because it's got the same height. So the question is, determine the work done. Well, if you remember, work changes energy, the work energy theorem, right? And because of the work energy theorem, if the kinetic energy change is 0, then that means that the work must also have been 0. All right? Easiest way to calculate that. All right, so our last question has to do with a force versus displacement graph again. And so if you remember, work is equal to the area of these force versus displacement graphs. Okay, so really all we need to do is evaluate the areas under these two graphs. So force number 1, we'll do this in purple, has an area of this shape. Okay, there's area 1. Force number 2, the scaling is all the same, so the y-axis is the same, the x-axis is the same, so that's good. And so I think for most of you, you should be able to just kind of visually inspect to see that the area 2 is bigger than area 1. Right? And so therefore the work associated with force number 2, because work is the area, has to be greater than the work of the first force. All right? In case you can't tell real close, real well, let me show you. I kind of superimpose these two graphs on top of each other. So right here you can see this is force 2 and 1. Force number 1 was the one that had a concave going up. So this one right here is force number 1. Force number 2 is this curve right here. Okay, and so force number 2, if you look at it for this is the area of force number 2, and clearly it does have a bigger area than the area of force number 1. Force number 1 is this line. So work 2 is greater than work 1. All right, that concludes the 15 questions for this unit. If you have any questions, pardon me. If you have any questions, just be sure to email me. Thanks a lot, guys. I'll talk to you later. Bye-bye.